and I'm replacing these old single pane, some of them broken windows that had plastic over them. One by one, I'm taking those down and hammering out all the rot and everything around on the outside, rebuilding sills, putting new trim in, new insulation, new caulking, everything. And a couple of them went in great. The others, well, a little bit less cooperative. I could have really used an oral surgeon for this.
Well, Dave, it is 7:01 and we are live on YouTube and recording. So if you're ready, I think we are ready. I'm going to just make some introductions and then turn it over to you. So thank you everyone for joining us this evening. The Tycho Commission is pleased to bring you this webinar, A New Climate on Both Large and Small Scales by meteorologist Dave Eichhorn. This presentation most likely would have been at our keynote address at our local government conference, which would have been today, but unfortunately we had to cancel again this year due to COVID. However, tonight Dave will discuss data related to climate change through a meteorological perspective and review how a warmer Arctic can impact our northeastern weather. He will also look at one of the region's big climate drivers, the El Nino-La Nina cycle in the Pacific, and investigate its role in the changing climate. And lastly, Mr. Eichhorn will explain the polar vortex. Is this a new catchphrase or is there something more to it? His message to local governments is generally to plan for more unpredictability in weather patterns. So first, some housekeeping items. You're all muted and have your videos off to reduce the load on the internet. Please put your questions and comments in the chat box, which you've already been doing very well. This webinar is being recorded and will be available shortly after tonight through our website and our YouTube channel. So now let me tell you a little bit more about our speaker before I hand it over to him. David Eichhorn is a meteorologist with over 30 years of experience who retired from Syracuse area television in April of 2016. More recently, Dave presented a keynote at the Commission's 2018 Black River Watershed Conference. We enjoyed it so much and the participants enjoyed it so much that we wanted to bring him back to a broader audience. As a meteorologist, Dave has won awards for severe weather coverage of the superstorm of March 1993, Hurricane Gloria, and for educating the public in the science of meteorology. While Dave is most widely known for his weather broadcasts on television, he has also expanded his work into lecturing and education, teaching at several colleges across central New York. Dave is a visiting professor at the SUNY College of Environmental Science and Forestry, where he teaches introductory meteorology and environmental meteorology. He is a full member of the American Meteorological Society. He has a specialized background in mesoscale or small scale atmospheric modeling and lake effect snow forecasting. Dave has a BS degree in environmental science from the SUNY Empire State College and a master's degree in environmental science from SUNY ESF. So with that, I will turn it over to Dave.
Thank you, Katie and Jennifer, for inviting me to this this Zoominar, I guess is probably a good thing to call it. So for those of you that are familiar with me from my television background, I've been retired since 2016. And what have I been doing with myself? Well, I didn't stop teaching at ESF for one thing. People constantly ask me, am I still in touch with the weather? Do I still keep track of things? And my answer is probably more now than I've done in my whole life. What's available to me now in the way of forecast material is far more sophisticated than anything that was available to me either on the internet or from where we used to buy some of our raw weather information when I worked at Channel 9 in Syracuse. What I have available to me blows all that away. And so it's just, what are you going to do? I mean, the information's there, the intrigue is there. And so before I do anything, when I wake up in the morning, I grab my computer, my iPad, I bring it over in my lap and I start looking at trends in atmospheric forecast models just from the previous 12 hours. And I'm on that at least twice a day. Rarely does a day go by where I don't spend some time just looking at what is going on the weather, both locally and more than both, locally, regionally, and sometimes on a planetary scale as well. It's one of those things where the more you watch, the better you get at understanding the little nuances that go on in the weather and what they mean with regard to the big picture of our weather coming up. And then the more sensitive you become to change. Like if I look at the models really carefully and I look outside, I'm watching the weather. I got a great weather station near my wood shop. If I see something that doesn't look like it should be happening, given what I've been expecting, that's sort of like a red flag. So I'll often stop whatever I'm doing. I'll leave the wood shop and come back inside and take a look at what's going on. I love that continuity. My wife, you're soon going to find out what my dinner conversations are like. I'm in my living room right now, and on my fireplace mantle, I've got a barograph, a recording barometer. I have a thermometer in 3 rooms in the house. I monitor air pressure and temperature right here in the house religiously. I've got weather equipment out right next to my horse pasture. No horses, just weather equipment. Who needs horses when you got weather equipment? This is terrible. If I was in a room with you watching you, I could at least gauge what I'm saying by your reaction, but I can't do that. So it's everywhere. It's all around me, and it's there all the time. So it's cool. So that's what I do. I also make furniture. When I was on television, my hours were such that I would go into work at 1 o'clock in the afternoon and not get home sometimes till routinely 12:30 in the morning, sometimes 2 or even 3 o'clock in the morning if I got working on a specific project. And that doesn't really lend itself much to a social life. When people were home, I was working. And when the weekends came, I had not seen my family all week. And so I really preferred to do that rather than go out and socialize. So in some respects, my job sort of forced me into sort of this hermit mode. But what that did, though, is it gave me the opportunity during the day to work down in my increasingly developing wood shop. And probably about 1/3 of the furniture in our house here now I've made. And I also sell my work. I've done commissions, good number of them. I'm a member of a co-op in Cazenovia, New York, Cazenovia Artisans, and I sell my furniture there. That's not meant to be a plug. That's just telling you what I do. So, all right. So I think what I'm going to do at this point is, unless there's some special tricks that I don't really know about, what I'm going to do is bring up my presentation to you, and I'm going to do a screen share, okay, which also eliminates any chance for me seeing the chat because I bring my presentation up full screen so that I can see it. So I will pause at times to entertain questions. And
Dave, we'll interrupt you if we see a question coming on the chat that we think you should answer right away.
Terrific. Okay, great. Thank you. Actually, I greatly appreciate that. All right, so let me do this. Let me do a screen share and bring that up. And I'm going to start my slideshow from the beginning. Oops, there we go. All right, so here's the gist of what I'm going to do today. It's not nearly as developed as it probably should be, but the more I got into this, the greater the number of slides, and I thought half of the audience is going to be snoring by the time I'm done here. So it's a bit compressed. And what I've talked about in the past, which we're going to build on a little bit today, is the following: that the climate has always changed. We know that. That's one of the things that makes climate itself intriguing. I mean, for many, 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 many thousands of years. But what's alarming a lot of scientists right now is the rate at which our climate is changing. And in particular, the rate with which, for me anyway, the rate with which the climate is changing in the Arctic. The Arctic's warming, I used to be able to say twice as fast as the rest of the planet, but now it's more like 2 to 4 times as fast as the rest of the planet. And the minute I found out about that in 2006, this light went on. It's like, oh, wait a minute now. I mean, just most fundamentally, like introductory meteorology, what drives the weather across our planet is the difference in temperature or the difference in heating from the sun between the equator and the poles. Because when we're really warm at the equator, really cold at the poles, that actually causes changes in atmospheric pressure in the upper atmosphere. And that in turn is what drives upper level winds, the jet stream, for example. And that's why during the winter, the jet stream roars along because the contrast between the Arctic and the pole or the equator is at its greatest. During the summer, when the Arctic warms considerably, and the equator only warms a tiny bit, then that difference in temperature diminishes. Winds in the upper atmosphere start to diminish somewhat as well. In fact, at times they diminish so much you can't even see the jet stream, the core of those upper level winds. And so when I found out that the Arctic was warming as much as it was kind of like, well, wait a minute here. I mean, that's got to be interfering with winds in the upper atmosphere over us here in the mid latitudes. It's got to be. That's one of the most fundamental things about meteorology. So what I did was I went into a number of user interfaces, climate user interfaces provided by NOAA. One in particular, I'm going to be sharing some output from with you tonight. And what it enables me to do is get away from the surface, meaning down near the earth, and look in the upper atmosphere. Look at temperatures in the upper atmosphere, look at winds, look at changes over long periods of time, decadal changes, okay? And sure enough, I was right. We've warmed enough down in the lower atmosphere in the Arctic to actually start influencing what's going on. Not 5, not 10, not 15, 20 to 30,000 feet into the upper parts of the troposphere, or what we call our winds aloft. So what I'm going to do today is talk to you about that, show you how that's impacting our weather in the mid-latitudes. And when we say mid-latitudes, we're talking, like the northern part of the United States, or even central part of the United States up into the southern part of Canada, roughly 30 to call it 60 degrees latitude. Okay, those are the mid-latitudes. All right, so the title of my presentation is still the same if you've heard me talk before. It's just the presentation itself has changed. Climate change through a meteorological perspective. And what I'm going to be presenting to you tonight is actually a stem off from what I use in one of my lectures toward the end of the semester at ESF. So climate change and changing weather, that's a difference. Climate is the long haul, okay? This is when we look at what has happened in the weather averaged out over long periods of time, as opposed to the weather, day to day, hour to hour. Good reason why Dave has a thermometer in so many rooms in the house and a barograph on top of my fireplace mantle. So I monitor the weather a lot, okay? And I also monitor the change in climate. So we're going to look at Arctic warming resulting in mid-latitude weather extremes. Now, when I say extreme, it doesn't necessarily mean extreme in an absolute sense, rather an extreme for our area. Okay, we don't get thunderstorms like they get in Oklahoma. A weak thunderstorm in Oklahoma would be a big deal here. Okay, I lived there for 5 years, I know. And so sometimes a weather extreme is nothing more than a spatial redistribution of weather. And therein lies what I believe is a lot of the problems in some of the weather extremes that we're going through here in the northeastern United States. So we're going to look at warming in the Arctic. We're going to relate that Arctic warmth to climate change and weather in the mid-latitudes and to a shifting jet stream, okay? And then we'll close out with some discussion on El Nino, although not nearly as developed as I wanted it to be, simply because the information's not there. And look at the northeastern United States regional and local impacts and some projections, okay? All right, first, a little weather background. This is your lesson in meteorology. We're going to talk about the connection between a warmer Arctic and high altitude winds over us. And those high altitude winds are big players in our day-to-day weather, okay? So jet stream winds aloft, 30 to 40,000 feet up, okay? So we're up there where commercial aircraft fly. And you've probably seen on television a million times the meteorologist showing the jet stream and it's dipping here and going to the north there, and what it means in terms of your weather. That's what we're talking about here. Jet stream winds 30 to 40,000 feet up. They generally flow above weather fronts down at the Earth's surface. What's a front? The front is the dividing line between warm and cold air masses. So look at this diagram here. I've got a jet stream shown with the shades of red and they're wiggling across North America. You should be able to see my mouse. Cold to the north and warm to the south. There's a reason for that. Underneath this jet stream in here, okay, is a front down at the ground. That's the dividing line between those two air masses. That's important to remember. And here's a neat graphic that I built actually for my class at ESF. I decided to import into the presentation. Here's a classic situation where the jet stream dips southward, shown by the reddish orange arrow here, through the Carolina or Tennessee and then northward up into New York State. That's where the steering currents in the upper atmosphere lie. It's beneath that our storm system, see the L, that's a low pressure, and the air flows counterclockwise around a low. It's beneath the jet stream where these lows develop and then track. As the low tracks, it pulls colder air down at the ground southward over poor people, like we're going to have beginning at about noon to 1 o'clock tomorrow, and warm air northward in advance of itself, like we had today. Okay, this actually is very similar to the weather that we've got going on right now. Okay, the reason why I'm showing you this is I want to establish a relationship. I want to make it salient to you that what goes on in the upper atmosphere is tightly related to what happens down close to the ground. Okay, so jet stream winds are the winds that steer, they develop and steer our storm systems down at the ground. All right, so the storms track underneath high altitude jet stream flow, but the jet stream flow itself moves. Let me back up. That dip in the jet stream right now, that dip, that trough in the upper atmosphere, it itself is moving eastward. It's bodily moving. And then on top of that, winds are flowing through it as it's moving. The winds are flowing through it a whole lot faster than it's moving, by the way. Okay, but the jet stream flow itself shifts. Okay, it's sort of like trying to follow a parcel of air through the jet stream is sort of like I was going to put a funny animation up for you. It's, you know, in that movie Harry Potter where they're walking up those stairs and the stairs are moving as they're walking, or like imagine yourself driving on a road, but the road's moving. The road's turning left, the road's turning right, and you're going through that road as it's wiggling along. That's what winds in the upper atmosphere do. Okay, so I'm going to give you an example, and hopefully this link will work. I'm going to take you to an atmospheric model. And I want to make sure there's no, good. Okay, there should be no, I have an account with this company and this is one of the ways I watch the weather and I want to make sure I log on so I don't get the ads. Okay, so
and we're not seeing it, Dave. We're still seeing your slide.
Oh, you are? Oh, okay.
You might have to unshare and then reshare the other pop-up. There you go.
Okay, let's try that. Thank you, Jenny. Or Kate. Who was that? It doesn't matter. Okay.
It's Katie.
Okay, screen share. And yeah, when I teach at school, I can bounce between the two, but apparently that doesn't work now. All right, we'll do this. Then I'll know to go back. Now you can see it, right? Okay. So,
yes.
All right, good. All right, so this is how the computer saw our world this morning. Okay, so Florida's down here, New York State is here, here's the US-Canadian border, and then Central America, Oklahoma, there's Oklahoma, Kansas and Missouri. Okay, so you kind of get a sense for where the United States is. These areas of orange and purple shading, okay, these are where the strongest winds are. This is the jet stream wind, and you're actually looking at two branches of the jet stream. The polar jet, okay, cold, moderate, very warm. This is the subtropical jet stream. So there's actually two of them going on right now. All right, what I'm going to do is just animate this forward. and show you what the computer is projecting as we go out in time for the next, I think this goes out either 10 or 14 days. And what I really want you to focus on is how these ridges and troughs in the jet stream themselves move. So we're moving this out every 3 hours. Soon it'll go to every 12 hours increments. So now we're in Saturday, Sunday, this coming Sunday, Monday, Tuesday, Wednesday, Thursday next week, Friday. So you can get a sense for how these ridges and troughs, they're really just waves in the atmosphere, how they propagate along. And the reason why I took the time to show you this is try and imagine a storm underneath the jet stream moving along as the jet stream itself is moving. So it's a very complex and very tightly integrated thing in the atmosphere. By the way, I want to stop here for a second. I want to show you something. Do you guys see this right here? You notice this? Jet stream dipping way south over us. Not good. And part of the reason it's doing that is because of a forecast blocking weather pattern to develop over the Northwest Atlantic, not far from Greenland. And we're going to talk about those blocks. There are weather systems in the upper atmosphere that would force the jet stream to dig to the south underneath them. Anyway, all right, so I'm off topic. So, all right, so now we'll go back to my PowerPoint presentation. And here we go. Okay, so you can all see this now. Okay, so all right, so your boring weather lesson is over. Okay, so jet stream, weather down at the ground. Why am I doing this? Because I'm going to show you very shortly how the Arctic is messing with those jet stream winds. A warmer Arctic has no choice but to be doing so, and that messes with the tracks and strengths of low pressure systems and their subsequent weather down at the ground. Okay, so now we're going to go to part 2, the Arctic. It's warming fast, and a warmer Arctic, again, forces changes in the jet stream. Sorry for the redundancy, but sometimes I get ahead of myself. All right, here's a map from 2007. And what you're looking at are global temperature anomalies. In other words, everywhere you see yellow, orange, and red is where the temperature was warmer on average for the year, okay, than normal. And if you look at the scale down at the bottom here, these are in, by the way, degrees Celsius. So when you get into the red, 2 to 4 degrees Celsius warm, that's actually a lot. That's like 4 to 8 degrees Fahrenheit above average for an annual temperature. That's a lot. So that's 2007. And the one thing that should stand out to you here, boldly so, is where is most of the warmth, the anomalous warmth occurring? It's in the Arctic. Now, I've shown this before, okay? But each year I keep adding to this. So what I'm going to do is step through this every year all the way up to 2020. So there's 2007, 2008, 2009, 2010, 2011, 12, little break for the Arctic in 2013, 2014, 2015, 2016, 17, 18, and for some reason 19 got buried. So we'll go to 2020. That's this year. Parts of Siberia this year were 6 degrees or more above Celsius, above average, while broadly the whole Arctic was very warm. I don't know if you guys heard, you probably knew this before I did, since I hardly watch any television now. There were a number of times where temperatures in Siberia were in the 80s this year. Wow. So when you take all those years and average them together, that's what you get, is this. Okay. So we've established that. I like to show these comparison pictures. This is the McCarty Glacier in the McCarty Fjords in southern Alaska in 2009. Okay, so if those graphics didn't make the warming in the Arctic salient to you, this will. Here's the same location in 2004. Back up, move forward. It's pretty amazing, isn't it? I love showing these. They really bring it home. This isn't 2009 or 19, what did I say? This is, yeah, not the early 1900s, okay? What you're seeing now is the Muir Glacier, and this is 1941. And here it is in 2004. Probably could update these. I wonder if this one would look even more impressive. So in 2017, I went up to Alaska on vacation with my wife. And we went into the what's known as the Turnagain Arm Glacier in southern Alaska, not far from Anchorage. And it was kind of cool because when you take these trips, they put you into this catamaran, and it's big. You're looking at the hull of the catamaran here as we're coming in on the glacier, and it was August 2017. And as you're going in, you're clunking this ice and whatnot, but these are big catamarans. I mean, they've got, there's an interior with tables, they serve food and the whole thing, and they'll hold, a couple, 300 people, I think. So, so we got on one of these cruises and went up to this fjord. And there we are in front of a glacier. Why did I put this in there? See, the television is still in them. Look, honey, as vain as ever. Anyway, no, I wanted to make this more salient to you because after we did our little photo ops outside, and I also shot a video, we went back into the cabin, and inside the cabin they have these monitors up all over the place, and it shows where you are. So our boat is here in the Turnagain Arm Fjord, right? And and then you've got the oceanographic chart, which is kind of cool. I enjoyed watching this because it's all GPS fed. And then I noticed as we turned around and we were on our way out, I said to the forest ranger who was the narrator, I said, "Why does it show us on the ice? If this is an accurate GPS map, we're not on the ice." He goes, "Oh, this software is from 3 years ago." Turned around.
Wow, interesting. Dave, we have a couple of comments. I just want to, you might not want to address them now, but just so you can
know where people's
minds are. First, someone, Paul, comments that he raced a canoe on the Yukon River in 2011, and the day they crossed the Arctic Circle, it was 90 degrees Fahrenheit.
Oh yeah.
And that, oh
yeah, go ahead.
And then I have another question that you might want to wait till. But should we be concerned enough about the warming in the Arctic that we should consider transitioning away from fossil fuels? All of our infrastructure has been built around fossil fuels. To transition away is a heavy lift.
Well, let's take a look at why the Arctic is warming so fast. And we'll cover that in a little bit. That might get us into that part of the conversation. So I'll defer just for the moment on that one, okay? So, well, here we go. The reasons for the Arctic warming are many, and honestly, from research that I've done, and I'll sometimes sit down and read these, articles, these peer-reviewed journals, and there's still a lot of research going on, but some of the more obvious ones is changes in winds from the mid-latitudes toward the poles. The atmosphere is starting to spend more time. This is hard to explain. So we looked at the jet stream and we showed it taking a big dip to the south and then shifting north. That's called a trough, and then it comes up around a ridge, okay? And normally, as you saw in that computer forecast map, those ridges and troughs propagate eastward across the atmosphere. They amplify, they de-amplify, they're always changing, which is why this whole thing is so interesting. What we're finding, though, is apparently there's pretty good research to support this right now. apparently the eastward propagation of those ridges and troughs are slowing down. That's hugely important because if a storm is tracking in that, imagine it moving along in the trough, coming northward toward New York State, okay? But the trough itself is also moving, which is normally a good thing for us because the storm would move over us, it would do its thing, but it would not only move northward, but eastward out of the way. So the progression of weather systems moves along much nicer, but as it turns out, as we warm in the Arctic and winds in the upper atmosphere beginning to slow down across the whole northern hemisphere, the propagation of those ridges and troughs is also slowing down. That means some of these storms are going to be a little bit slower to move out, and I'll show you the consequences of that in just a minute. So anyway, let me back up. My wife just came home, so my Bernese Mountain Dog's going to be probably pretty bouncy here in a second. So, the reasons for the warming in the Arctic, there are many. Changes in winds from the mid-latitudes to the poles. So this meridional flow of south to north and north to south, but particularly south to north, is actually advecting, transporting warmer and warmer air up into higher latitudes, okay? So we're seeing changes in atmospheric and to some extent, even some oceanic circulation. The other is increased carbon dioxide in the atmosphere and other greenhouse gases. The chemistry just doesn't get any more basic than this. The Earth is constantly radiating heat out into space, more so during the day than at night, okay, because we're warmer during the day from the sun. Well, the wavelength, the infrared radiation with which the Earth radiates out into space, turns out the so-called greenhouse gases, in particular carbon dioxide and methane, they're very sensitive to that particular wavelength of energy that the Earth radiates back out into space. They're sensitive in the sense that when those wavelengths of warmth hit them, their molecular structure, they become more excited. How's that? They gain more kinetic energy. And so what they do is they take that radiation and re-emit it in all directions, some out into space, some sideways, some back down to Earth. Okay, so as carbon dioxide in particular increases in the atmosphere, there is going to be more re-emittance of that radiation back down to Earth. There's kind of like no way around that. That's just a very fundamental basic thing in chemistry. And the Arctic is seemingly taking one for the team. Winds in the stratosphere. So the lowest part of the atmosphere that our weather occurs in is called the troposphere, okay? And above that, in the stratosphere, temperature is actually warm. And that's because in the stratosphere, we've got good ozone up there, good kind of ozone. It's absorbing ultraviolet radiation from the sun and it warms the stratosphere. But by virtue of its warming, it sort of creates a lid and stops weather down near the Earth from building out of this lowest layer of the atmosphere. So why is that important? Winds in the stratosphere during the winter buzz around in one big circle. That, in fact, actually is the polar vortex, okay? What you're hearing about in the news every time we get a cold outbreak, oh, it's the polar vortex. No, actually, the real polar vortex sits up in the stratosphere, but what it sometimes does, and it's been doing so a little bit more since about the year 2000 now in frequency, is it sometimes splits. It breaks up, and the minute that happens, there's a feedback from that down into, of all places, the Arctic. And so when the true polar vortex breaks up, we call it a sudden stratospheric warming, it means bad news for us because down in the mid-latitudes, because the Arctic goes through a period of excessive warmth and whatever is up there comes down. Now, when I say excessive warmth, that's relative to them, okay? Their warmth is still darn cold for us when it gets transported southward. So when the stratosphere goes through those burps, if you will, okay, there often are bursts of warming in patterns yeah, just warm patterns in the Arctic, and we often pay a price for that, which I think we are going to be doing soon again, unfortunately. Okay, so, and also increased air pollution. The Arctic's, the heat that would normally, the Arctic just constantly giving off heat into the atmosphere. And so with more cloud cover, more humidity, more air pollution, the Arctic's just not the heat sink, the heat loser that it once was. And I strongly encourage you to go to this link. If you just Google NOAA Arctic report card, okay? They'll probably far more eloquently tell you the same things that I'm telling you now with nice graphics and pictures. So I strongly recommend it. So here's how a warmer Arctic messes with the jet stream. So here's the normal jet stream flowing across. Here's its average position. So we're taking out the ridges and troughs. Here's its average position. And normally to the north of that, the weather is very cold. Just to the south of it, the weather's somewhat moderate. And even farther south, with the tropical air where it's quite warm. So what happens is this: when we become warmer in the Arctic, like all those maps I showed you going all the way back, and I just arbitrarily started in 2007. I hope that got the point across. When we're warmer than normal in the Arctic, okay, the jet stream has to shift south. And the reason why it has to shift south is the jet stream lives above temperature contrast down at the ground. It helps to create temperature contrast, but temperature contrast also, it's chicken and the egg thing, helps keep the jet stream stronger. So when it's not as cold up north, the jet stream does shift south, which leads us to this. You're looking at the North Pole, and down here is United States, North America, there's Alaska, and there is the North Pole. Everywhere you see yellow, orange, and red in here is where the jet stream winds in the upper atmosphere have actually increased. And so what I did was I took 2001 to 2015 and I subtracted out the 15 years of 1985 to 2000. So you take one period, you subtract out another, anywhere you've had an increase in wind, it shows. Well, is that really an increase in wind, or is that a wholesale redistribution of the jet stream? Guess. The jet stream's spending more time over us. How much of an increase is it? About a 2-knot increase. And you might think 2 knots, come on, Dave. Well, actually, that's when you look at the average of the winds, both summer and winter, you find out that 2 knots is a 5 to 6% change in winds over us. So locally, our winds in the upper atmosphere have actually increased. The jet stream spending more time over us. No, wait a minute, Dave. Didn't you just point out earlier that below the jet stream is where fronts and storms hang out? The answer is yes. More jet stream time over us means more battles between warm and cold air, more storms tracking over us, more weather. So winds in the upper atmosphere aren't just shifting south, but if you ignore our area and look at the whole hemisphere, from the equator to the poles, they've actually started weakening. So for the moment, there's 2 things going on. Winds in the upper atmosphere broadly are slowing down, but locally, they're cranking right along. So the question that comes to my mind is, does that mean that us here in the mid-latitudes, we're going to be like taking one for the team here? And the answer is yes. By the way, here's the raw data. The whole hemisphere, northern hemisphere, from the equator to the poles, it varies year to year. You can actually see the slowdown taking place. This comes off one of those NOAA websites I told you about. Broadly speaking, weaker winds aloft mean weaker weather systems down at the Earth's surface. Not so, I guess, for those of us that live right underneath where the jet stream is spending more time. And weaker winds aloft also means slower weather systems. I wanted to break off for a minute and get into this. Thunderstorms. During the warm season, the jet stream weakens, storms near the ground weaken. Everything just kind of slows down. And so what makes our rainfall, which is so critical to agriculture, are afternoon summer thunderstorms. Thunderstorms need wind in the upper atmosphere. It's critical for them. And yes, that is me standing in front of an F4 tornado in Oklahoma. Thunderstorms are made of strong updrafts. And when those updrafts build up to the top of the troposphere and hit the stratosphere where the atmosphere is really stable, they flatten out on top. Here's a really cool shot of one. That's an anvil. That's a thunderstorm. That's a big thunderstorm shot from the space shuttle. So what you're looking at is thunderstorms are made of updrafts, building towering cumulus clouds. They hit the stratosphere. And when you have good winds up above, it helps to remove that air that's coming off the ground and strip it away, which encourages more updraft and keeps the storm going. So in parts of the world that rely on thunderstorm activity in that ventilation, as we call it, the tops of the storms, if winds in the upper atmosphere start slowing down, our thunderstorms are not going to be as productive in making rainfall as they've been. Again, just driving that point home. Okay, now wait a minute. So if a warmer Arctic means a weaker jet stream, weaker winds in the upper atmosphere, then shouldn't our thunderstorms also be weaker? If they're not as strong, maybe that's not so bad. But wait a minute. Shouldn't weather systems not only be weaker, but also slower moving? What if the thunderstorm over you isn't as strong as it would otherwise be, but let's say it stays over you for a longer period of time? What if it back builds, tries to move out of its genesis area and the back edge of the thunderstorm rebuilds? One terrible story, it is probably my worst night in television, was July, I forgot the year now, it was either 2014 or 2015. And we were, I used to, when I left the TV station, finally in 2016, I was doing 14 weather broadcasts at night. They were for other markets besides just Syracuse, out of our studio. So sister stations in Watertown and Binghamton, Utica, Syracuse, they were all closing up their news operations. So we wound up doing their weather for them. And in order to get it all done for everybody, a lot of this had to be pre-recorded by an hour or so. And it was around 9 o'clock in the evening, and I was all set up to do the Binghamton weather broadcast, and you had to hit it. You had to hit it on that mark. Meanwhile, this thunderstorm exploded over downtown Syracuse and then started moving eastward into the east side of the Syracuse. You could hear the thunder outside the studio. As the storm began to move away, it was moving so slowly, big rain producer, that on the backside of it, new storms were developing. So as the storm would start to move out, it was back building. The net effect was for downtown Syracuse to become inundated in water. And I couldn't do a thing about, I couldn't go on the air. Not that I could change it, but I could at least inform people. Even more importantly is I didn't like being distracted by what I was doing and not able to follow what was going on. Do you remember? That's the storm where the person got sucked down the manhole cover and died. And not that we could have saved that life or anything, but it speaks to the extremity of slower moving thunderstorms. And so now try and imagine, well, I'll save the rest of that for later because all right. So, you know what, I'm going to skip this. Unless I'm in person, that slide is going to be a hard one to go over. So with the jet stream changing speed, direction, and location, weather over us changes as well. Many places are now getting what used to be somebody else's weather. And that's hugely important. That thunderstorm that was over Syracuse that night, would that have been an extreme, say if it were located over southern Ohio? Or in an absolute sense, would it have been extreme? Heck no, right? I mean, some of those storms in the Southern Plains, like the pictures I just showed you a moment ago, they're really bad. But locally, it was an extreme. So our weather extremes are not only extreme intensively, but also geographically. Remember last summer how dry it was? Hey, where'd all our rain go? Other parts were flooding. Where'd all this rain come from?
So Dave, that kind of relates to a question we have from someone in Parrish, northern Oswego County. Why do places like Parrish seem to be in a constant state of drought with drying wells and trickling streams?
Well, it's not just places like Parrish. So if these changes in the jet stream are slower moving, I mean, all I've been focusing on, here I am guilty of being a meteorologist. What am I focusing on? The weather that's over you. What about if you're getting terrible weather, somebody downstream's getting wonderful weather? Wonderful, lasting, wonderful. Remember last summer? Yeah, water pressure lowering in a lot of wells. I have a pond on my property now, and it was so low that my neighbor came over and said, you really probably should go around and inspect the containment of that water. I've never seen it that low. And so, and again, I'm going to speak purely through a meteorological perspective. There are other answers to your question. But with slower moving features in the atmosphere, it more often than not now, when we get into a particular mode, you might say, we're more likely to stay in it. That may not be the answer you're looking for, but I guess there are a lot of reasons why we were in a drought last summer as well.
I do remember last summer, Dave, and how it was sunny and warm for so long. It was very unusual for this area.
Yeah, and what's interesting also is, it wasn't a record for days over 90 degrees. But the problem is that the number 90 is arbitrary if you think about it. Like, was it any kind of a record for days over 80, for example, or for the amount of sunshine we had, or and I don't have answers to those, by the way. So the jet stream pattern winds, I keep saying the jet stream, there was hardly any jet stream around last summer for one thing. But what we did have in the way of jet stream winds was in a pattern that it was conducive to keeping dry air, not just sunny weather, but dry air. You can be sunny and humid, and we've had more humid summers than last year. I mean, it had its moments, but a lot of last summer was actually somewhat dry in terms of whether it was humid or not, just hot and dry. And one of the things that's starting to make me wonder about this coming summer right now is the pattern that we've had for the last 2 or 3 weeks has actually been dry, with the exception of what we had finally had some rain, right, yesterday. It's been dry, and what's setting up actually isn't too different from what we left off with last year. So it's like, oh no. So anyway.
So a related question, Dave. When you think about agriculture and food production and where we grow our food, are there climate models that project what that might mean for our area in terms of food production?
Actually, yes. And I've got a little bit of that coming up for you very shortly.
I'll stop interrupting.
Oh, no. Please do. Please do. Okay. So, and also I have this tendency to get off on tangents, and I want to try and stay to a reasonable amount of time for you people. Some extreme examples when our weather systems slow down, and examples of blocking weather patterns. So, here. What's a block? Right. This is a map of the jet stream, and you see it dipping down over the northeastern United States around an L. That's a storm system. Oh, excuse me. In this day and age, we call it a polar vortex. I'm having some fun right now. I can do it because I'm not on the air anymore. And then it rises sharply northward over Greenland. See that? And what it's doing is it's moving around this big high pressure in the upper atmosphere. We call it a blocking high. When these highs develop, the general west to east flow across North America, across the Northern Hemisphere gets disrupted. It literally blocks the flow. And so what it does is it forces the jet stream south, and then we'll end up with something like this. Some of our best, more severe lake effect situations have come in a flow pattern like this, big blocking high over Greenland. When I see that develop, it's like, oh no. Some examples coming up here. So when that flow comes down along the whole Great Lakes region, it's not good because it aligns itself along the Great Lakes. So you end up with a situation like on this satellite picture, from Lake Superior down across Lake Huron and then feeding a band off Lake Ontario. And this particular day it was snowing 3 to 5 inches an hour, just south of Oswego, across central Oswego County, and then points eastward, probably not too far from Utica. And this was lake effect that was actually fed. Look at this satellite image. This is streamers of lake effect clouds coming off Lake Superior, but one main band right there. Jennifer, you can see my mouse, right?
Yes, we can see it.
Okay, all right, good. And then crossing Lake Ontario. So one of the things that happens is instead of Lake Ontario having to put all this energy into the atmosphere to make snow, some of that work's already done for it by the upper Great Lakes, and the upper Great Lakes lake effect snow throw tons of ice crystals into the atmosphere, which help seed the clouds over Lake Ontario. It's a lean, mean lake effect machine, and it's a lean, mean lake effect team, you might say. It's a team effort, and we wind up with a butt of it downwind. I love showing this. Yeah, you guys, how many of you remember this? In Parrish, 2004? I got another one for you in case you don't. This was a result of that blocking pattern over Greenland. And research, there's a big debate out right now whether atmospheric blocking over Greenland is actually on the increase or not. Seemed like it was a shoo-in a little while ago, but there's some good scientific debate about it at the moment. So why am I bringing this up? I'm bringing this up because blocks, again, we go back to when winds in the upper atmosphere start to slow down hemispherically, those ridges and troughs and blocks don't move so fast. They stick around. 2007. There you go. There you go, Parrish. Remember that? 144 inches of snow in North Redfield in 9 days. That was because of one of those blocks. Oh, interestingly enough, just prior to this, we have been really warm, and the Great Lakes were warmer than average. So it was a confluence of anomalies. You have Great Lakes that are warmer than average, and then all of a sudden this block develops, and here comes like the perfect storm for lake effect snow. So a lot of energy released into the atmosphere. So when blocks develop, things slow down. This is a winter consequence of things not moving along. Those are cars, by the way, in the Oswego parking lot outside Waterbury and Scales Hall. Hurricane Sandy. So Hurricane Sandy starts off in the Caribbean, and almost a week in advance, I was doing freelance reporting for Syracuse.com, and I called Stan Lindhorst and said, Stan, I want to do an article on what I think may turn out to be a really, really big storm for the Northeast coming up. And he goes, well, when? I said, well, it's about next Friday, about a week out. Well, Dave, why don't we wait till we're a little bit closer to the event? And I what can I say to my editor, right? He called me on Thursday to say, oh my God, you're right. This was the pattern in the upper atmosphere prior to Sandy. Look at the size of that block. The hurricane tracks north, it weakens into a tropical storm, then explodes as it becomes what we call extratropical, and it can't go north because of the block. East winds around this thing turn it straight inland into the Northeast. That was a block. So as internal, so what I'm going to do now is bring this into the Northeast. And and then I think what I'd like to do is open this up to a few questions. Is internal forcing greenhouse gases and external forcing sort of duke it out? I mean, come on, the sun is still there. It's still doing what the sun does. It's still at certain angles at times of the year and times of the day. It's the atmosphere is going to try and do its best, constantly try and do its best to get back to normal, but it's having a hard time doing so. And so we've got this sort of duking it out, you might say, between internal forcing, okay, and more variability in internal forcing and then just the atmosphere trying to be normal, meaning more variability in our weather. Okay, so I showed this when I presented before. This is an updated version here that I thought you might find interesting. So there's this something called a climate extremes index. It's a website by NOAA and it's terrific. And what if you take the northeastern part of the United States and you take all the weather systems in the Northeast, all the weather stations, okay, that have been in existence for 100 years, and you say, okay, if you have a weather extreme, meaning more than 2 in statistics, standard deviations from the normal, so it's really extreme, okay, we put a red flag on you. But if it's just you and nobody else gets that extreme, it doesn't count that much. So this graph is that. This graph represents the whole northeastern part of the United States, and everywhere you see these shades of red are where larger and larger areas experienced those weather extremes. So it doesn't measure the extremity, it's the size of the area affected by it. And look what's gone on here since 1910. And again, they're only using data from weather stations that have been around for 100 years. And these, so what extreme are we looking at? I'm sorry. These are extremes of maximum temperature. When the maximum temperature goes more than 2 standard deviations above normal, bang, a bell rings. And when a whole lot of stations also go through that, we just probably have one of those today. Well, wait a minute here. Wait a minute. This graphic is northeast extremes in minimum temperature. When minimum temperatures are 2 standard deviations above normal, that means overnight low temperatures. When they're 2 standard deviations, that shows up, but only if it happens to a lot of people. Pretty interesting, isn't it? And by the way, this website, this is a terrific website to go through. It's quite intuitive. How about extremes in one-day precipitation? The only thing I noticed in this, it was quite variable in the past. Seemed to go through a dip around 1980 and then started heading up. And more, particularly over the last 10 years now, we're seeing more of a consistency of one-day precip events showing up over 20% of the northeastern United States. So I don't know, trying to find a trend in here might be a bit of a stretch right now. We'll see. But that said, extremes in drought. Look at this. 1, 2. There's definite increase in extremes in drought. In 2000, I think it was 11, my friend, I was an avid fly fisherman, Bob, got a hold of me in August. And did you just hear that bell? Did you hear that?
I did hear a bell.
Okay, we have a service bell on the floor near our dog. He wants his dinner. Yeah, he's hungry. He wants his dinner. Oh God, sorry about that. I'm getting a little giddy. Anyway, so my friend Bob in August is complaining because the Delaware is below, way below or no, I think it was in the spring. That's right, because this was during the Mayfly, the Axogenia. And that was the same year we had the flooding rains later on in the year, where the water near my dock up in the Adirondacks was up over the dock level. So what this says is that within a given year, it's very easy to have extremes in both precipitation and drought. And these seem to be showing up a little bit more now. All right. So
can I ask you a question? One of the questions while you're at that point, we have a question about with our lower snow totals this year. Do you believe we might be in for another drought with or without the possibility of higher summer temperatures?
Yeah, my answer is yes. And actually, I'm sort of keenly aware of what's going on. So what I've been doing is I'm doing some consulting work for some people that are monitoring water flow into one of the Finger Lakes. And what they're looking for is they're measuring turbidity, and they're looking for where this turbidity flows into the lake. And what they're trying to do is get drone video over this particular lake, looking down where they can not only take video of it, but there's scientific instruments in the drone that measure things that I don't really know a whole lot about. So my job as a meteorologist is to try and find them really good, like snowmelt runoff events or precipitation events. And it's been like this for, I mean, I started working with them just before Christmas, and we had high hopes with all the snowpack that we just had of a real decent runoff event. And it wasn't that at all. As a matter of fact, the ground was able to absorb a lot of the water from the snowpack. I mean, there was runoff, don't get me wrong. And rivers and streams are probably flowing beautifully right now. But the air has been so dry. We've lost a lot of snow due to evaporation. We've lost the rate with which snow was melting in previous warm days was slowed up because the air was so dry. Do you guys know about that? When the air is dry, so let's say you have a snowpack and the temperature outside is 40 degrees. Now the snow doesn't get any colder than 32 degrees, right? So you have 40-degree air moving over the snow. So in theory, the snow should be melting. But if that air is bone dry, then the air blows over the snow surface and there's evaporation of that melt of that water and that skin surface of the snow. Evaporation is a cooling process. It slows up the rate with which that 40 degrees would otherwise be able to melt the snow. And so it's dry. Yeah. And I'm still waiting for a decent rain event for these people. Anyway, all right, back on track.
Another question too is, are the extremes in drought, or perhaps even this image you're showing about heavy precipitation, are they reflective of the patterns and the slowing of the systems and the storms passing rather than the one-day weather event extremes?
Yeah, my answer I think is yes. And I mean, if you're slowing, think about this. I mean, the two are not unrelated necessarily. If you have a weather system that so it's a one-day precip extreme, right? So what if one place, so let's suppose you got a front, like what's going to come through here around noon tomorrow, okay? That thing's going to blast right through here, colder air rushing south through the Midwest right now, okay? That's going to blast through here tomorrow. It's going to come, we're going to get some rain with it, maybe some thunder tomorrow, okay? And out it goes, all right? Not atypical for March, right? It's a windy month. But if that front one's going slower, or if it's stalled even temporarily, so that it could manufacture more thunderstorms, then in that 24-hour period, midnight to midnight, you could have a one-day precipitation extreme from either a widespread event or maybe a multitude of individual thunderstorms tracking over the same area. Yeah, good perspective. So 100-year events, well, you know, Northeast. We're getting more of them than any other part of the United States. And again, what I want to do, and I know some of this is, everything I'm telling you is supported by research. What I'm trying to do is get this package down so that it's, hopefully a little more understandable. So yeah, slower moving weather systems, slower moving ridges and troughs because of broad, slower moving flow in the atmosphere. And yet superimposed on top of that, ironically, the storm track spending a little bit more time over us. Projected end of the century relative to the same 1981 to 2000 period. What's the likelihood of these 100-year events? And atmospheric models going forward in time are projecting the Northeast, basically a continuation of what we're going through now. 4 times more likely. More likely. Why us? I threw this in. Well, because storms generally track southwest to northeast over the eastern parts of North America. That has to do with its geography, land versus ocean. And so oceanic storms that thrive on warmth and moisture in the ocean in contrast with cold continental air, the Northeast has always been kind of taking one for the team. Remember that expression, Eastern Canada is often the graveyard for nor'easters. So now just take this and superimpose our changing climate on it. All right, so here's what I'm going to do before I get to this, because I'm just about done. I want to stop the screen share just for a minute and give you time for some questions about this, things we haven't gone over yet, and go ahead and fire away at me. I can open up the chat here so you can see it as well.
Yeah, and I've been reading some of them. Here's one. Is there any data to tell us the rate of climate change during the end of or beginning of the previous ice ages?
Well, yeah. Paleontological data from, you name it, tree rings, exoskeletons in marine sediment, ice core samples. We've actually got a pretty good record, and the resolution of that record has improved greatly just in the last 10 or 15 years, because our ability to look into the ice cores on a more molecular level has improved a great deal as well. So one thing that is also clear looking at past history is that we've gone through periods of abrupt climate change as well, where the kind of change that we're experiencing right now that might you see a projection that would take you to the end of the century, a quarter or even half century. Sometimes some of these changes has occurred.
How many years do you have to analyze to establish climate?
Well, it depends on what you're looking for. NOAA is routinely, it's a 30-year period is what we consider our present day climate. So like, for example, you saw, we were comparing everything relative to the 1981 to 2000 year, 2010 year period. That's a 30-year period. And every 10 years, our record changes. And we look at the previous 30 years. So this year, we're going to be looking at 1991 to 2010 as our basis for comparison. Some of the data I showed you actually use the whole last century. And that, like when we look at climate extremes, you can't say you're having an extreme event unless you have a long period of record to compare it to. That's one thing. As climate scientists, choose your period of time, geologic time, thousands of years. It really depends. But when we talk about the norms of the average for the Syracuse area, for example, it's the previous 3 decades.
Okay, thank you. People are kind of wanting to talk a little bit more about the current conversations about climate change and New York, I think taking some big steps to reduce greenhouse gas emissions, I think people are trying to understand what your thoughts are on that. How seriously do we have to take this? What's it going to take to maybe stop some of the effects that we're seeing?
Some creative leadership. I know that's may seem a little trite, but and the reason why I phrase it that way is, like, years ago, our corporate CEO guy came down from Seattle to the TV station, and he really kind of blew me away with this. He said that, we have a whole group of TV stations around the United States, and we're giving you, as well as every one of the rest of them, their own autonomy to be creative. You know your market better than anybody else. And now this is less related to your question, but it'll lead up to an answer. But here's what I want from you. Each one of you stations, and he was talking to us, so he said that I want you to be responsibly creative. And what he meant by that is, look, we're not rolling in cash, okay? But think out of the box, be creative. And then I'll add, let's get back to science, all right? And try and more objectively understand what it is we're up against, so that we're not just randomly shooting from the hip making policy decisions. And I think this is where climate scientists, and I'll throw in meteorologists now, really need to have some time to debate. Like, for example, the influence of the Arctic on the mid-latitudes, okay? I very carefully stayed away from a couple of topics. There has been a lot of research and debate over, well, the reduction of sea ice in the Arctic. That's having an impact. At the end, our ice cap is getting every year smaller and smaller and smaller and smaller, and to the point where we're hovering around record territory almost every year now, and sometimes breaking the record. So I shouldn't say smaller and smaller, but you get what I'm saying. And there's a lot of research that's gone out saying, wow, with less ice in the Arctic, when we get into the cold season, then you've got all this open water, and it's got to be feedbacking into the atmosphere and causing this and this and this. And there's actually good solid research saying that the theory might be sound, but we don't have the evidence to support that. And it's good research that says we don't have the evidence. But I'm not looking at Arctic sea ice. I'm looking at the warmer Arctic period and its influence in the upper atmosphere. And there is so much research out there right now that, I blew by them in the PowerPoint, but I had some citations in there. And actually, I got 2 pages. Jennifer, I don't know how you can have this for people to see and review. And the bibliography at the end of this is fresh. It's real. You can't bring parity in temperature between the equator and the poles and not have an impact mid-latitude winds. You just can't do it. So, that's a fundamental rule in meteorology. So, I hope I didn't get too far off track.
No, I'm glad you mentioned the Arctic blue ice, sea ice, because there were some questions related to that I think you just touched on by mentioning that.
But here's the vulnerability of science. Good science is the null hypothesis, which means you have a theory and then you go all out and try to prove it wrong. That's sort of a backwards way of going into it, but that's what good research is. If you can't prove it wrong, then hey, maybe, there's something to your theory. And in science should be allowed for debate. And because somebody disagrees with something, it doesn't mean that whatever they're disagreeing with is wrong. It may be that they're adding a new perspective to it, but that's what makes science whole. And it blows my mind that we debate the influence of carbon dioxide in the atmosphere, and yet when our cell phone rings, we pick it up and we expect the call to be there. Why? Because it rang. And we're talking to somebody like we're talking with our Dick Tracy watches, and we expect that to work. That's believable, and yet some of us cannot understand that carbon dioxide is a terrific re-emitter of long-wave radiation from the Earth's surface. Sometimes it's like, wow. But so that's why we need to give science some room to breathe here and play a role in this. Okay, go ahead.
Thank you. No, it's 8:15, so we probably can just take a couple more questions. We've got a question about, you mentioned the rate of change early on as a concern. Are past changes in the ice cores and in those other examples as abrupt?
No, absolutely not. The changes that we're seeing in global average temperature, it's like, oh, we're 1/10 of a degree higher than we were. Well, what we're accomplishing since the industrial age is what it took millennia to do with natural climate variation in the past. So no, the pace with which we're going through is vastly accelerated. And well, okay, that answers your question.
And another question, where'd it go? What is the possibility of sudden, unpredictable major shifts in global atmospheric patterns that could change weather patterns much more significantly?
Oh, wow. You know what that is? Abrupt climate change. What is the possibility? Well, it has happened in the past. We know that. Okay. And actually, for many years, many years, like a couple thousand or more, we've had very little instances of abrupt climate change. So we have adapted, nature's adapted, and we have adapted to an environment that's really quite stable. The idea of abrupt climate change just naturally occurring on its own should always be a consideration. And I think that one that might be amplified, a probability that such an event might be more likely as a result of our input into the changing climate needs to be a concern, needs to be a consideration. So let me do this. I got one more thing I want to show you. Is that okay? All right. Yeah, I'm going to cut this a little bit shorter than I wanted. Okay. This. I wanted to bring this up because somebody asked about snowfall. So this is a graph of the snowfall in Syracuse. I updated this to include last year. And the trend line there is not a good trend line because there's so much variability year to year. That's the point of this graph. Year to year variability. It itself is increasing.
Yep.
You can see it. And a friend of mine at Syracuse University, went into the raw data to make sure that I wasn't just whistling Dixie. I mean, and so, so my point is this, and really, I wanted to try and express this a little bit more strongly so earlier, is that in preparations for our future, in policymaking, in agriculture, we, at the very least, need to start preparing for, I hate to use the expression, but it is true, weather extremes, more variability. It's going to put stresses on our ecosystem. Things that have evolved and selected over many years under a moderate climate, they're going to be under a lot of stress. I think we will be under a lot of stress. Cities or urban environments that have combined sewer overflows, for example, are not going to be able to handle what would be an extreme for this local area. So I think we need to be prepared for that. Support research in agriculture such that we can grow crops that can better handle longer dry periods, or that are more adaptable to various kinds of dry or for that matter, flooding. So all right.
Just one other question. How much CO2 and other greenhouse gases are emitted from volcanoes and other natural sources versus that sources that are generated from man-made sources?
I know the number's small, but I don't have hard numbers in my mind. They're really not that. They used to be, millions of years ago it used to be, but then again, we weren't around. And which also reminds me that, if you try and think about what the climate might have been like many, many millions of years ago, please keep in mind that the continents weren't where they are now. It was a different world. Okay. As one geologist very kindly reminded me. Okay.
I think we've got most of the questions. Jen, do you see any other questions?
There was one question about El Nino, and if we know the effects of those, the La Nina, El Nino, on what's the implications for us.
Okay, so for the sake of brevity, I wanted to spend more time on this, and I apologize. I was a little bit long-winded tonight, but the El Nino, what is El Nino? El Nino is a warming in the tropical Pacific. Okay, and so when an El Nino develops, what it does, in the most simplest form, is it pumps heat into the atmosphere in places where the atmosphere is not normally heated. That interferes with winds in the upper atmosphere over the Pacific, which then affect us downstream. Okay, and El Ninos typically last for a year, and then they change phase. They go to a period of El Nino neutral, and then we go into the opposite phase, which is what we are in right now, a La Nina. Okay, that's where this tropical Pacific is colder than normal. And when we are and I wanted to dwell on this a little bit, when you go into spring and summer during a La Nina, thunderstorms across the southern plains, there's a greater probability of tornadic thunderstorms, not just the southern plains. And there is also a greater probability, I'd have to look this up now, I'm pretty sure the parts of the United States that are can normally depend on pretty persistent precipitation are much more prone to drought. So that's something to keep an eye on this year.
And we have a question, it's kind of a lengthy question from Landon, who is a meteorology student at SUNY Oswego, doing a climate hydrologic study on the precipitation and rising levels of the Lake Ontario Basin. Through this study, he says, we are looking at not only the climate impact and overall assessment, but how factors such as the lake levels may have influenced current weather events. Have you noticed any anomalies or new general precipitation trends that may have been influenced or resulted by increased precipitation or rising lake levels? Also, how might factors such as an increase in water in the Lake Ontario water basin interact with more local scale weather patterns for the upstate area?
Well, all right. The easy answer to that is that I've not been paying attention to that. But think about this though, the basin, right? Any lake basin is shaped like this, right? So, with the increased water level, you're going to have much more surface area of water. Okay, so I've got to believe that is going to have some sort of an impact downstream. For those of us that are east of Lake Ontario and the Tug Hill, for example, I'll bet it's going to be interesting to see what happens, because once the lake, that is really an interesting question, because as I think about that, and the lake starts to heat back up, going through its normal cycle, right? End of summer thunderstorms that are generated by the lake. Do we get more of them? Are you going to get more water in the Tug now? Are we going to have more issues? It's a good question, really good question. And then superimpose that on the background of a drier climate that we're in right now. Or I'm sorry, drier regime. I shouldn't say climate, but it's dry. And so, good question, really good question. And that's the only answer I had for you. Sorry.
Okay, I think that is pretty much it. We're going to 8:30. I think we're losing a few people, which I understand.
Yeah.
So any final words, or if not, thank you very much.
Yeah, thank you for having me on, and I appreciate the opportunity to talk and give some meteorological insight. It's always a challenge when you're doing it this way, with graphics, and if we don't walk away from this with anything, just keep it in mind that there's stuff going on way up north that is impacting our weather here. Things are slowing down broadly across the whole northern hemisphere. We are going to hear of more Houston type flooding events, hurricanes that stall because they can't get picked up by winds in the upper atmosphere and moved along, and so on. So that's the world we're in.
All right. Well, thanks everybody for coming out tonight. There's lots of thank yous and great presentations in the chat. So and like Jen said, it is recorded and it's on our YouTube channel, so you can share it with others.
Yeah, thanks for inviting me. This has been a real pleasure. And next time, let's do this in person.
Let's do that in person. Thanks for coming back.
All right.
Putting up with us again. So thank you.
All right. Have a good night.
Dave. Thank you.
All right. Bye.
Good night.